Hey y'all, welcome back. So today we are going to be looking at something called a series. So last time we looked at something called a sequence, which is an ordered list of numbers. Specifically, we looked at two different types of sequences. We looked at arithmetic sequences and geometric sequences. Today we're going to look at something called a series, which is what you get when you add up all the terms of a sequence. We're also going to be looking at a partial sum, which is when you only add up those first so many terms. So let's get on into it, and we'll go over what a series is. So a series, like I said, is a sum of a sequence. And we could talk about a partial sum, like a fourth partial sum, for instance, and that would be the sum of the first term through the fourth term. So for example, let's say I asked for the third partial sum. What that means is I'm asking for you to add the first three terms. So if this is the sequence I'm given, 3n minus 2, let's start by identifying the first three terms. So a sub 1, let's see here, a sub 1, there we go, would be, let's see, if I plug in 1, so like 3 times 1 minus 2, that would give me 3 minus 2 is 1. A sub 2 would be 3 times 2 minus 2, so that'd be 6 minus 2, which is 4. And then finally, a sub 3 would be 3 times 3, which is 9, minus 2, oops, let's make that look nice. 3 times 3, which is 9, minus 2 is 7. So the first three terms here are 1, 4, and 7. And so when I'm asking for the third partial sum, what I'm really asking for is the sum of the first three terms. Okay, so the third partial sum rather would be a sub 1 plus a sub 2 plus a sub 3. And as we just saw, that's going to be 1 plus 4 plus 7, which would be 5, and 7 is 12. So the third partial sum of this series is 12. So that's pretty easy, right? You're just literally adding numbers together. You just have to make sure that you find the correct values first. Now, there's a better way of writing this. And so I'm going to introduce to you some new notation on how you can write a series or a sum, whether it's a partial sum or just an infinite sum. And this is called summation notation. Let's just delete this, boom. And this is how you would write it. Okay, so this looks kind of funky. So let me kind of break down what all these things mean. This big E looking letter right here is actually a Greek letter, and the way you read it is called sigma. And in general, in mathematics, sigma means sum. Okay, so what this is effectively telling you to do is sum up the first term to the third term. So this number on the bottom here, that is known as the lower limit of summation. In other words, that is the number of the first term you're supposed to add up, and then the number of the last term you're supposed to add up is called the upper limit of summation. So that's this number right here. So that exact same question that I asked up here, what is the third partial sum of that sequence, can be written like this, where I'm saying find the sum of this sequence from 1 to 3. So this is the actual sequence right here. This is the sequence to be, well, I'll just call it the sequence. So that's what all these different things mean, and it's a lot easier to write this question by just not even writing any words and just using this notation. This is really common notation that you'll use a lot next year in calculus, so it's important that you start to become familiar with it. Now, this can get a little tricky because take a look at this one. Consider the partial sum. This would be the 1,000th partial sum of just the sequence n. So this sequence is pretty, pretty straightforward here, but let me kind of break it down for you. When it's just n, that means that like the first term is 1, the second term is 2, and so forth. So what this is really asking you to do is to add up all of the term, basically all the positive integers from 1 to 1,000. The first term would be 1, the second term is 2, the third term is 3, the fourth term is 4, and you just keep going on until you get all the way to the end. So let's say we got a little bit closer to the end. We only need 3 there. So let's say we got like, 996, 997, 998, 999, and finally we get to 1,000. Okay. We probably don't need that many. And so I want you to add all these up. Now this can be pretty tedious, right? So, even if you had a calculator doing 1 plus 2 plus 3, entering in and just making sure you didn't accidentally type in something wrong, that could take a long time. So to compensate for that, we are going to try to look for a little pattern that exists here. And this little pattern can be used to find the finite or the partial sum of any arithmetic sequence. Take a look here. Let's say we were to rearrange these. So what's like 1 plus 1,000? Right? 1 plus 1,000 is 1,001. Okay? So like if I were to just add those two first, I got 1,001. If I were to add 2 and 99, what's 2 plus 99? Well, 2 plus, not 99, 999 is also 1,001. Okay. Huh. What about 3 plus 998? 3 plus 998 is also 1,001. You could probably see where this is going. Okay, 4 plus 997 is, as you might expect at this point, 1,001. So what I want you to notice here is that when you have an arithmetic sequence, you can group the terms in this way to find basically pairs of numbers that all add up to be the same thing. So if I were to, if you think, okay, there's 1,000 numbers in this list, 1 to 1,000. If I pair them up, how many pairs are you going to have? Like, here's a pair, here's a pair, here's a pair. How many of those would you have? Well, you'd have exactly half of them, right? So I would have 50 pairs. Okay, so I'm going to just make a note here. There's 50. Well, here, let's not do an equation here because I'm going to type this out. 50 pairs of 1,001. Okay, so another way to compute this is to say, okay, well, this is actually a lot easier to calculate than typing in all the numbers. We could just do, find the sum of the first and the last term, which is 1,001, and multiply that by the number of pairs. In other words, 50 times 1,001 will give us our solution. I'm going to have to break out the calculator to do that. You might not have to, but it's, we're still going to use the calculator a little bit here. So we get 50,050. So that means this sum is 50,050. Now, what would be nice is if we could generalize this idea. And so that we could come up with some kind of formula so that no matter what the arithmetic sequence is, we can compute it in a similar way. So this is, the question here is how can we compute this a little bit more efficiently? Well, we found out how to compute this one. Let's see if we can generalize that a little bit. Just going to bring this down. Let's get a little bit more room here to write. Okay. So for the sum of a finite arithmetic sequence, if I can write here, geez. For the sum of an arithmetic sequence written in this form, and I'll sort of write a generic version of this, if it'll let me. Let's see what our options here. I might just have to actually draw it out. Okay. Yeah, no big deal. Okay, so let's say we go from 1 to k. Okay. if I go from 1 to k and I've got an arithmetic sequence, so the variables that we used last time is we used d for the common difference, n is for our independent variable, and then we said a sub 0. Okay, so if it's written like this, his common difference, 0th term or a seed value, and then this is just n, this would be the upper limit up here, so this could be whatever you want it to be. What this is going to equal is, now let's go back up and kind of think through how we did this, right? We found, first of all, how many pairs were there? There were 50 pairs. That was equal to half the number of values that we are calculating. So half of k would be k over 2, right? So that's half of k. So that's the number of pairs. And then we want to find like the sum of, where do we get this 1001? Well, we added the first and the last pair. Okay, so I'm going to add a sub 1 and a sub k, because in this generic case, k is going to be our last term number rather. All right, so this is our formula right here. I'll even zoom in on it so you can kind of look at it a little bit easier. So just to break this down just a little bit more, okay, D is the common difference. Okay, a sub 0 is pretty self-explanatory. That's just the 0th term. Then we have k, which is the number of values. So what I'm going to do here is actually just say this k divided by 2, just to make sense of why that is divided by 2, is because we are grouping pairs. So this is how many pairs of terms. Okay, there's half of the number of terms. So like if you have 100 socks, you have 50 pairs of socks. And then so we're going to multiply that by the sum of the first term and the last term. See if I can squeeze that on there. All right, so that's it. Like if I just plug in my values here, I can compute that pretty easily. So like for example, let's say I give you an equation like, I'll just throw one kind of random out here. So let's say I wanted to find like the first 100 terms of 2n plus 7, right? So to compute that, I would say, okay, well, how many pairs are there? There's 100 values, so there's 50 pairs, times the sum of the first term and the last term. So if I plug in 1, I get 2 plus 7 is 9. And if I plug in 100, I get 200 plus 7 is 207. And then I can just multiply, or add these up and multiply. So I have 9 plus 207 is 216, and 216 times 50 is 10,800. So if you have that formula, it becomes pretty easy to compute these sums. But what if the first one isn't actually a sub 1? Like what if I don't actually start at the first term, but I start at a different number? Okay, what happens when the lower limit of summation isn't 1? So let's say we got this crazy partial sum. Now, you would not want to do this by hand, and what I mean by that is you wouldn't want to like plug in 643, plug in 644, plug in 645, and go all the way up to 721 and just like by hand add those numbers, right? So we're going to use this little shortcut. But what I want to do is I want to generalize even this. Okay, so I'm going to even take this to the next level. This will work if we start at 1. If we don't start at 1, then we're still going to use basically the same formula, but what we have to realize is that this should be half the number of pairs, right? So if I start somewhere else, like instead of starting at 1, let's say I start at 10, or we'll just call it, what would be a good letter here? Kind of hesitate to use L because that looks like 1. Let's use P. Okay, so let's say we're going from P to K. So the total number of values here is going to be, it's kind of weird here, but K minus P plus 1. Okay, the reason why it's not just K minus P, not the difference, let's take a look up here. Like if I did 1,000 minus 1, I would get 999. But the problem there is that there's actually 1,000 numbers here. So when you're counting, like you're saying 1,000, well, you're counting from 1 to 1,000, and you don't want to leave anything out. So you have to make sure that you account for that first number. So this is just going to calculate exactly what it did before, which is the number of pairs there are. Now, don't get freaked out if, like, for some reason you have an odd number of pairs, or I'm sorry, an odd number of terms. This will come out to be something 0.5, and that's okay. The formula will still work out for you. So over here, we're not interested in the first term anymore. We're interested in the pth term, so a sub p. So that's really the only change we have to make, okay, is the way we calculate how many pairs there are, and we're going to recalculate the first value. Okay. There is another way to do it, and I'll show you both ways so you can kind of determine, you know, what's best for you. But let's compute this partial sum with this formula. So we've got, let me just highlight the actual formula part here. Let's see. There we go. So this will equal the upper limit minus the lower limit, so 721 minus, I think that says 648, and then plus 1, or 643 rather. So this will calculate how many pairs there are. The value of the first term would be what I get when I substitute 643 into this sequence. So 5 times 643 plus 7 would be 3,222. The value of the final term when I substitute 721 in, let's see, times 5 plus 7 gives me 3,612. So this is going to be how much each pair is worth, and then we're going to multiply that by the number of pairs, just like we did in this 1,000 example. So, you know, I'm using a calculator to do all this. Don't think I'm like a genius or anything trying to do this in my head. So I'm just going to type this in, 721 minus 643 plus 1 divided by 2, and I get actually 39. I'm kind of glad I got 0.5 here. So we get 39.5, so that's how many pairs there are, 39 and a half, because I guess we have an odd number of values. And then times 3,222 plus 3,612 is 6,834. So when I multiply those two together, I should get my overall sum, which is this lovely number, 269,943. So if you're using the formula, you know, it's really just making sure that you plug in all the correct numbers there. There is another way you could handle this to where you don't have to know this other equation, where you could just rely on this one. I don't necessarily think it's any easier. In fact, it might be more work, but you know, everyone has their own little thing. So let's say, you know, I want to rewrite this. One way to consider this is, let's say I have a bunch of numbers. Okay, so let's say all this little scribble scrabble over here is just all the values, right? And let's say the sum, so like we want just the sum from 643 to 721. So let's say that right here, this is where 643 is, the 643th term, and then we have the 721st term is all the way at the end, and we have 0. Now, I'm not writing any numbers here because I really just want to kind of get a point across here about how this other technique is going to work. What we want to do is actually just add all the terms from 643 to 721, right? So what we could do is we could actually find the sum from, well, I guess not 0 because we're not starting at 0, my bad. Let me erase that. I don't want to cause confusion there. We are actually starting with 1. So let's say we wanted to compute this. Another way we could do it is we could find the sum from 1 to 721, find the sum from 1 to 643, and then just subtract these, right? Like if I take the length of this and subtract the length of this, I'm left with just what's in here. Okay, so this, if you do this and you were starting at 1 with with both sequences, and your equation would look something like this. Here we go. So you'd have sort of the bigger one first, okay, where we're going from 1 to 721. And the sequence there is still 5n plus 7, that doesn't change. And then we want to subtract, and this is where it gets a little cool, we want to subtract the one from 1 to 643. And what that will do is that will give us, and maybe we want to put parentheses around here just to make it, you don't usually have to, but.
Mr. Schiller?
So anyway, so we can calculate these separately. Let me scroll up just a little bit here to give me a little bit more room. We would want to compute both of these separately. So let me go ahead and steal this little equation over here. And we'll say minus the other one. Okay, now these are actually going to be different k's. And, you know, I'm not going to write this generically, but let's see. So 721, 643. So 721, 643. And then let's go ahead and compute these values right here. So the first term here, if I plug in 1, would be 12. That's going to be true in both cases. And then the 721st term was, what was it, 3,000, we got it up here, 3,612, and the 643rd term was 3,222. Now, at this point, probably putting everything in the calculator. I'm not going to bother with that. And what I see is I get the exact same thing. So just to recap this, there's two ways that we can calculate these partial sums if the sequence is arithmetic and we're not starting at 1. One way is just to use this new sort of generalized formula, but if you want to use the old school formula where you're starting at 1, you can. You just have to split it up and find the difference between these two different sequences. I changed this little scribble scrabble to make it look a little bit more like what I'm trying to talk about. So in any way, the idea here is you'd find the sum from 1 to 721 and take away the sum from 1 to 643. You get the same answer both ways. Honestly, like if you can get your head around this more generalized formula, you know, obviously it's a lot simpler arithmetically and just typing it in your calculator and that sort of thing. So you have a couple options there, so you can kind of pick which one you like. Now, so far we've looked at finite series, but what about an infinite series? What if there's no upper limit here, where it just goes on forever? Well, let's think about what would happen here in an arithmetic series. You know, if I want to find the infinite series of 2n from 1 to infinity, I could just, to get an idea of what's happening, I could just start plugging numbers in. So like if I plug in 1, I get 2. And the rest of this sequence should be pretty obvious, right? You're just multiplying 2 by the input, so, or the term number. So it would be 2, 4, 6, 8, 10, 12, etc. So the sum would be 2 plus 4 plus 6 plus 8 plus 10 plus 12, and you would like keep going on, right? What you might notice is that these numbers are just getting bigger and bigger and bigger, and as I add them, you're going to have the same effect where it just goes to infinity. Okay, so we don't want to say that it equals infinity. That's kind of bad. It's just not true from a technical standpoint. An expression cannot equal infinity. We can tend towards infinity. That's something we can do. We can say that we're diverging, And we'll get into converging, diverging next time, but for now, we'll just say there's no sum. For an arithmetic sequence, infinite arithmetic series have no sum. There's no answer here, okay? So you could just say, no answer, no sum, there's no sum. Anything along those lines will be good. No solution. I wouldn't really say no solution because we're not looking to solve an equation, but something along those lines. Okay, there's basically no answer. So if there's no upper limit on if you have an infinite arithmetic series, there's just no sum. Now later on we might talk about, okay, well, should we distinguish something like this from something like this, where we got, and I'm just going to handwrite this real quick just to let's make it red, just for speed's sake. Okay, so let's say we had the sum from 1 to infinity, but of negative 2n, right? So in other words, we want to find an infinite sum of progressively more and more negative numbers. So like the sum here would be something like -2, -4, -6, -8, -10, etc. Not plus. I said minus, typed plus. My finger's on the wrong key, my bad. Something like this, right? Where this is going to trend towards negative infinity. So you have something trending towards positive infinity, something trending towards negative infinity. For now, for today, we're not going to distinguish between these two, but we will in the future. So just something to keep in mind that while there is no sum here, we do want to eventually keep track of whether or not, if we are diverging towards positive infinity or negative infinity. And like I said, that's something we'll talk about next time. When you have a finite geometric series, or let's just talk about geometric series in general, particularly the finite ones, unfortunately for a finite geometric series, we don't have a shortcut like we did with the arithmetic ones. Okay, so I am not likely to give you one that has a very large upper limit because that's just going to take too long to evaluate. So here we're just going to have to evaluate it by hand. I know that's kind of annoying, but that's just how you're going to work this one out when you have a finite geometric series. I guess the good news is you don't have to memorize anything or have to reference anything. You literally just plug in all the numbers between 1 and 4 and then add them up. So not a lot of brain power here. You just, if you're using a calculator, you just type it all in. We get 3 plus 9 plus, let's see, times 3 would be 27 plus 81. And then this is where calculator starts coming out. 3 plus 9 plus 27 plus 81. I got 120. So not a lot for me to talk about here. If you've got a finite geometric series, this one's not that particularly interesting. Yeah, it just is what it is. You'll just calculate it out by hand. And when I say by hand, I mean no shortcuts. So that's the finite one. But what's a lot more interesting, in my opinion, is the infinite geometric series. So let's look at this. This is going to be a little bit more worth talking about. So for the infinite geometric series, first reaction might be, well, we have the same issue, right? Like if we're just adding an infinite number of positive values, it should be infinity. But that's not always the case. It may not be infinity when you're adding smaller and smaller values. So this is something that I think is not very intuitive. So let me try to explain what's going on with this one. Okay, so we've got the infinite sum. Oh wait, partial sum. No. That is not a partial sum at all. In fact, I'm kind of wondering if I made that mistake on previous problems on the, I'm just going to say consider. Yeah, get rid of that. That's just bad. That's embarrassing. Yeah, remember, it's not a partial sum if you got infinity up here. I'm wondering if I did the same thing up here. Yeah, no, that's a partial sum. Okay, so that's good. Yeah, so no, it's just my bad. It's just that's the only time that happened. So consider this series. So let's figure out what this actually means. If I plug in 1 here, I'm going to get 1/2. This is going to be 1/2, and then I'm going to add. Okay, if I plug in 2, I get 1/2 squared, which is 1/4. And if I plug in 3, I get 1/8. And then 1/16, and so forth. And I'm going to add this forever. And my claim is that this is actually going to equal something. So, equal some finite value. So let me try to convince you before I tell you what it equals by drawing a little shape over here. I'm going to draw a square. Okay? Nice little square. And I don't really, well, that's fine. Okay, so let's say, for argument's sake, that this square is a 1 by 1 square. Okay, so like this is 1 and this is 1. Okay, just to keep the numbers real simple. Okay, so now what I'm going to do is I'm going to fill in an area that is equivalent to this first term, which is 1/2. Okay, so half the square. Let's change colors here. We'll go to green. See if I can get it right on there. I'm probably going to struggle too much. It's not even worth getting exact. Okay, so here we go. So let's say, I'm just kind of estimating here. I'm not measuring it for real. But let's say that they're, well, let's at least cover the whole thing. Come on now. All right, that's about as close as I'm going to get. Okay, so let's say then this is 1/2. Right? So that's half of the square. Yeah. And then let's say, okay, well, I have half of that, which is 1/4. Right? So 1/4 would be like this, right? Let's see if I can, and I'm, again, just estimating here. I'm not actually breaking out the ruler. Okay, so this would be 1/4. So 1/2 plus 1/4 is is 3/4. So we're up to 3/4 so far. So now let's do another one that's half of that, which is 1/8, and that will make up like this little piece, right? Half of a fourth is an eighth, no surprise. Okay, so there is, oh, nope, come on, there we go, 1/8. Hopefully you can start to see like where this is going, where I'm going to take this. Okay, I'm going to divide this next section in half to get 1/16. So let's pick, let's see, we're running out of colors here. How about some light blue? So this section right here is going to be 1/16. And basically you could continue this forever. And if and only if I continue it forever, will I get my sum. Okay? So my sum here is going to be what? What do you think it's going to be? Oh, let's not do the same color, because then we're not going to be able to see the different squares. So this one would be like 1/32, and then we've got like, let's do a black one here. Then we got 1/60. Oh, no, I don't know why I didn't save my color. Let's do like, what other colors do we have to work with here? Oh, let's go with the brown. So we'll say right here is 1/32, and basically you could just keep this going forever until you finally fill it up. Let's see, let's get a real bright one. You know, basically continue this pattern on 1/2 plus 1/4 plus 1/8 plus 1/16, and you could just keep going further and further in, and then eventually you will have filled up the entire square. Now, since this is a 1 by 1 square, we can see that, okay, well, the area should be pretty obvious. The area is going to be 1. You know, basically you're going to keep adding these areas. And so the point I'm trying to get at here is that the area of this square is 1. And so the sum of this infinite geometric series is going to be exactly 1. Okay? Not 0.999999. It would be a little bit less than 1 if you didn't add up all the terms. But if you added up all infinitely many terms here, you would get exactly 1. That's pretty incredible, I think. I do not think that that is, you know, very intuitive. You know, to add up to add up an infinite number of positive values and be left with a finite result, I think is something that can, kind of hurt your brain a little bit. But it should make sense. Like, let's say I had something like, let's say I had the sum, let's do a little sum here. Let's say I had the sum from 1 to infinity of 1/10 to the power of n. So in other words, like 1/10 to the power of n. So another way to think about this is like, okay, well, this is a geometric series, quite obviously, because we're raising something to the nth power here. And that's our multiplier is 1/10. So let's just like plug in a few numbers and see what happens. So if I plug in 1, I get 1/10, which is, as a decimal, 0.1. If I plug in 2, I get 1/100th. So that would be plus 0.01. If I go to 3, I get 0.001, 0.0001, 0.0001, and so forth. So you can see that when I like stack these up, like if I were to stack them up and add them like you would like in elementary school, start with 0.1 and then 0.01 and then 0.001, and you just keep going. What you'll see pretty quickly is that the sum here should be 0.111111 repeating, because you're just going to keep adding these ones, and you'll get 0.1111, and then you just keep going on. So then the question is, okay, well, what is that? What's 0.1 repeating? And then 0.1 repeating is exactly 1/9. Okay, 2/9 is 0.2 repeating, 3/9 is 0.3 repeating, 5/9 0.5 repeating, 9/9 is 0.9 repeating, but 9/9 also equals 1. So does 9/9, 9/9 equals 1, and 9/9 is 0.9 repeating. Huh, it's kind of weird, but also true. 0.9 repeating is 1. Just let that sink in for a minute. All right, so anyway, let's get rid of that. I don't want to confuse you today. So anyway, the point I'm trying to make here is that it is possible to have a series that's infinite that actually has a finite value. So this doesn't always happen, though. As you can imagine, you could pick a different R value here, different common ratio that would make this not work. So like if I had something like 2 to the n, well then if I had 2 to the n, then my series would be 2 plus 2 squared is 4, plus 2 squared cubed is 8, plus 2 to the 4th is 16, and so on. And this turns into something that's obviously going to go off to infinity, right? As these numbers get bigger and bigger and bigger, then it's just going to get bigger and bigger and bigger. So where do we draw the line? How do we know if there's going to be a sum or not? Well, it all has to do with this common ratio. If the absolute value of this common ratio is 1, less than 1. In other words, if you basically have a fraction in here, whether it's positive or negative doesn't make a difference. But if you've got a fraction here that's smaller than 1, then you will have a sum. There is a sum, and I'll show you how to calculate it in a minute. Then the sum exists. It means we have an answer. Hooray! Okay. If the absolute value of R is greater than or equal to 1, so starting at 1 and then going up, like the example I gave was 2, then there is no sum. All right, so there's just no answer. So if I ask you a question like find the infinite series for the sequence 2 to the n, you just say R is bigger than 1, so there's no sum, and I'm done. So how do we calculate this? All right, this I think deserves a little bit of explanation here, but let me just give you the formula up front, and then if you're curious, you can listen to the full explanation. If not, you can just fast forward that part. So let's say we've got a sum that is a infinite geometric series. Oops. Okay, so we got an infinite geometric series We need infinity up at the top. We're going to start at 1. And then our sort of template for our geometric series is a sub 0 times r to the n. I wonder if there's a shortcut to make that subscript. I'm not really sure about that. Okay, so here's my geometric series. And so here's the formula to calculate the answer here. It's actually a pretty simple formula here. The first term, that a sub 1, again with the subscript. All right, a sub 1 divided by 1 minus the common ratio. That's it. That's your equation right there. This is this right there. Okay, so the big question is like, okay, well, where does this come from? Why does this actually work? So I'm going to kind of go through the proof right here. Again, if you don't really care, you can skip past this part. But if you're curious why this is true, I'll try to explain it. So here we go. So let's say we have this sequence. I'm sorry, this series. So this is a little proof here. So the way we would sort of add this up, quote unquote, by hand would be to actually plug in all the values. So like if I plugged in 1, I would get a sub 1. Right? I'd get the first term. Let's see. Come on, subscript. You'll be the death of me over here. Oh, come on. There we go. Right, I'm just going to highlight that because I'm going to need that over and over again. Okay, plus, then we would multiply that first term by the common ratio. So we'd say times r. And then to get the next term, we would multiply the common ratio again. So we would say, oh, okay, all right, what happened? All right, come back. There we go. Okay, we didn't save everything. That's okay. So we got a1 plus. Then we're going to multiply the common ratio by that first term. And we'll do it again. So this time we have to multiply it twice. So it'd be like r squared. Ooh, there we go. And then we'd multiply it again. And basically you would do this forever. Yep. All right, so this is basically the definition of what a series is. I haven't really done anything. Just start with the first term, then multiply by the common ratio, multiply the common ratio again and again and again. So I could rearrange this, okay? In fact, what I'm going to do just to make this a little simpler, well, I'll just leave that in there actually. What I can do is I can actually I can multiply both sides by r. Okay, so if I multiply both sides by r, this is not something I think you would expect to do, but I would multiply this by r. Okay, so then each one of these terms gets multiplied by r. Yeah, so this become r squared, and so forth. All right. So basically, I multiplied both sides by r. I get this. Okay. Now, from here, and this is where it gets a little funky, I can subtract this from the original sum. Okay? So what I mean by that is on both sides, and it looks like I got a little extra plus in there, from both sides, I'm going to subtract this from the original sum. So I'm going to take this and subtract both sides, okay, and then all this should be in parentheses, right? Okay, I'm starting to run out of a little room on my proof here, but I think I can make it fit. So I'm just going to drag this up just to give me a little bit more space here. Okay, so do y'all see what I did there? I subtracted both sides of the equation from the original sum. Now, this original sum is the a sub 1 plus a sub 1r, blah, blah, blah. Basically what I'm doing is I'm taking this entire first statement and then subtracting the second statement. Okay? So notice that both of these sums have basically the same sequence, except this first one just has that a sub 1. It's like one extra term. So what I'm left with, this whole right side, is just going to end up being a sub 1. So this whole thing is just a sub 1. Okay. Now, what I could do at this point is I could factor out my sum like a GCF. And I'm kind of running out of room here, so I'm going to give myself a little bit more room over here. Anyway, I'm going to factor out the GCF, which is this whole sum I've got highlighted here. And what I'd be left on the inside would be 1 minus r. And I bet you can see where this is all going. Okay, now to solve for the sum again, this is really what I want, is I'm trying to explain where this formula is even coming from, is I would divide both sides by 1 minus r. Now, you don't really need to know this proof. I'm never going to test you on this proof or anything like that. I just think it's kind of cool to know where some of these formulas come from, and some of them are just worth going through because the proof itself is not terribly complicated. But yeah, there you go. So now we have our proof. So we've got our formula here, and I showed you where it's coming from. Really, you don't need to do all this though. I mean, as long as you know what the formula is, that can get you through most of the problems. So let's sum up here. Okay, we've talked about a lot. Let's summarize what we've discussed so far. So we saw that for both arithmetic and geometric series, there are ways that we can compute the sums. So for a finite arithmetic series, we are going to use this formula. Didn't like that one. Let's try that again. Highlight this, go down here. There we go. Okay, so for a finite arithmetic series, we're going to use this if we start with 1. Okay, if you start at anything else, then you're going to want to modify this equation a little bit. Instead of starting at 1, we're going to start at, we'll say, what letter did we use above? I thought it was P maybe. Yeah, so we'll use this one. In fact, maybe I should include the rest of the formula here. Okay, so we'll use this equation right here. So this will be when n is not 1. And you're probably getting a headache seeing me scroll up and down so much. So I'll try to cut that out if I remember. All right, anyway. So this is if you start with 1. This is if you do not start with 1. You can see the formulas are very similar. So this would be if you did not start with 1. With another number. Or, you know what? We'll just say P, if you start with P. Because that's what we use down here. Okay, so in other words, like, here's the formula right here if you start with 1. Here's the formula if you start with something else. And this is K minus. Kind of hard to see that. I'm not sure if that's going to come up in the video. All right, for an infinite arithmetic series, there is no sum. All right. For a finite geometric series, okay, they will have a sum, but there's no shortcuts. You just have to add them up. Okay, so unfortunately, that's kind of annoying, but it is what it is. For the infinite geometric series, if that ratio, or the absolute value of that ratio, is less than 1, we've got a formula. If the absolute value of the ratio is greater than or equal to 1, then there is just no sum. Okay, so let's focus on what we can actually, whoa, calm down there. Let's focus on what we can actually compute here, which is this infinite geometric series, and that's this formula that we proved up here. There we go. Right here. That's the money. All right, so let me just put that up. I'll leave that up for a few seconds so that, if you're going to take like a screenshot or something, it's a little easier. But yeah, so just to kind of sum up here, if it's a finite arithmetic series, yeah, you can use one of these two formulas depending on what you start with. Infinite arithmetic series, where there's nothing to do because there's no sum, it'll be either infinite, it'll trend towards infinity or negative infinity. For the finite geometric series, no shortcuts, you just got to add them up, and then for the infinite ones, you can use this little formula down here. Okay, that is only if the common ratio is less than 1. If it's bigger than 1, then there's nothing to do. Okay, before I let you go here, let's just look at a few examples, okay, and see if we can compute these. So for this one, this is where we do not start with 1, so we're going to have to use this formula up here, and this is arithmetic, right? Looks like a mx plus b kind of deal here. So we want, wrong one, I pulled the wrong one. Here we go, that's the one we want. Okay, so for this first one, let's calculate, let's see, we'll have k minus p, so that's 7 minus 3 plus 1. 7 minus 3 is 4, plus 1 is 5, so we got 2.5 pairs. And then if I plug in 7, let's see, 24 minus 21 is 3. And if I plug in 3, I get 24 minus 9, which is 15. So yeah, that would be 15. And then, so I'm going to throw all that in my calculator here. 2.5 times 18 is going to give me 45. And that would be my answer. So just making sure you got the right equation. You should be good. Oh, wait a minute. Oh, yeah, that's right. Okay, so over here we've got an infinite arithmetic series, which, as we know, has no sum. So there's nothing to do. We just say there is no sum for now. For the next one, we have a finite geometric series. So this is one where we just have to compute each term individually and kind of hope for the best here. So if I plug in 1, I have to determine what's a third of 2,187, and that would be 729. And then I'm going to just keep multiplying 1/3 by that. So times 1/3 or divide by 3 will give me 243. And I got to get the first 7 terms. This is going to be pretty tedious, but there's not really a way around it. So we've got 243 divided by 3 is 81. Divided by 3 is going to be 27. Divided by 3 is going to be 9. Divided by 3 is 3. So how many do we have so far? 1, 2, 3, 4, 5, 6. So we need one more. And that's going to be 1/3. Or no, actually just be 1. 3 divided by 3 is 1. The next one would be 1/3. Okay, so this is my a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub 6, a sub 7. So got them all taken care of. Now I just need to add them up. So, and I'm using a calculator at the side here. 729 plus 243 plus 81 plus 27 plus 9 plus 3 plus 1 gives me 1,093. This next one's an infinite geometric series. So we've got to decide first, does it have a sum? So I look at the common ratio and I see that it is less than 1. So we will be guaranteed a sum here. And we're going to use this little formula right here. Okay, so the value of the first term, when I plug in 1, is going to be 729. Actually, this is actually the same sequence that we had over here, so we can reference this without having to recalculate everything. And then we have 1 minus the common ratio, which is 1/3. So this is something that I'm going to just throw in the calculator. Now this, I think, might be worth pulling up the calculator so you can see how I input it. So I'm going to create a fraction here. Let's get out of all this. Create a fraction and do 729 over 1 minus 1/3. And the reason why I'm using this fraction thing instead of just like using parentheses and make it one long line is so that my answer is given to me as a fraction. Oh, it didn't give it to me as a fraction. That's interesting. What's up with that? Huh. That's weird. Okay, wait a minute. 1 minus 1/3 would be 2/3, right? So 729 divided, do I get the same thing, 2/3? Oh, I guess I ought to, because it'd actually be 729 times 3 divided by 2. Oh, that's weird. I don't know why it's not given to me as a fraction. I'm even asking for it. Maybe the numbers are too big. I don't know. I don't know what's going on here with the calculator. I was hoping it would give it to me as a fraction, but it doesn't like that. So, okay, no big deal. It is a terminating decimal, so we don't have to worry too much. So our answer here is going to be 1093.5. All right, enough of that. That calculator was not as helpful as I thought it was going to be. I thought it was going to give us the fraction. I'm not sure what's going on there. Usually it does. All right, so our last but not least example problem here is looks like we've got a geometric sequence, but we have a problem here, and that is that this geometric sequence has a common ratio that is bigger than 1. I'm just trying to move this box over here to make it look nice. There we go. This number right here, this 4, that's bigger than 1, which means that this sequence is going to diverge to infinity, because we're just going to add bigger and bigger and bigger numbers with no bound. So this is another case where there's just no sum. Okay, and you could say exactly that, just there's no sum. All right, guys, well, that's it for today. I hope you guys learned something here about infinite and finite geometric and arithmetic series. So just to kind of sum up here one last time, a series is what you get when you add up the terms in a sequence. We can talk about partial sums, which is when you don't add all infinitely many of them. Instead, you're adding like some finite number of them. There are formulas for some of these series, specifically the finite arithmetic series and the infinite geometric series when the absolute value of r is less than 1. But other than that, there's not really any formulas. Like, for instance, if you find an infinite arithmetic series, you just know there's going to be no sum. If you have a finite geometric series, you just have to add them up the old-fashioned way. And if you have a geometric series where the common ratio or the absolute value of the common ratio is less than greater than 1, then there's just no sum. So that's it for today. We'll talk more about converging and diverging series next time. Y'all have a great day.